Yeah, thank you, Viorel. I will summarize some of the great work that has been done in subtask 1.1. Let me see. Yeah. The main focus will be the work in subtask 1.1, and if we have time, I can go a little bit in the research we do here at research in relation to degradation modes. Right now, there's an effort to get out a report on what are the degradation modes in the newer or the newest solar cell and module technologies that are already commercialized or in this process of being commercialized or being developed. I will, since there's a lot of work going on there, I will focus on 4 of these and go into details. So the first one is PID. This work is spearheaded by Peter Hake and some of the colleagues there, including us. For those of you who are not aware about PID, all modules that are installed and operating in the field are being stressed by the voltage. There's a voltage between the frame that is grounded for safety and the cells themselves. And this voltage, depending on the polarity, causes a stress on the cells that, depending on the type of cells, the temperature, humidity, the conductivity of the surface, the soiling on the surface, can cause no or some degradation. In the past, this degradation was quite significant. Many of you may be familiar with PID shunting. This is the most common PID for the last decade or so, which was caused primarily by ions, sodium ions, migrating from the front glass into the junction and creating defects. And if for some types of modules, this would cause quite a lot of performance degradation in a span of months and years. And it was mostly on the negative side of the string. So that was one of the important acceleration factors. But the industry learned from that. We developed accelerated testing for it, and measures were implemented in the newer modules to prevent this. So now we have quite PIDS resistant modules like the newest ones. But you can see this is a graph from 2015. Quite a lot of plants in Europe and all over the world had problems with PID shunting because it was not so known and it was not part of the qualification testing of the modules that were being sold at that time. This history tends to repeat itself a little bit. A new but old PID mode called PID polarization was actually the first one that was discovered in 2005 in SunPower IBC cells. Wasn't really a problem for aluminum back surface cells, but once bifacial PERC became a thing, like Nicholas showed that it increased in the last few years, it showed that these bifacial PERC were actually sensitive on the rear side, causing quite fast degradation of the rear side performance, whereas the front side was not so affected. So again, a new cycle of testing and improvement of the modules was made. Now, the newest technology that is being commercialized is N-type solar cells, TOPCon, and it looks like these are also sensitive to PID. Some of the details change. Instead of being the rear side, the front side of N-type modules and TOPCons is degrading faster. It could be for PERT, could be both the rear side and the front side is affected by degradation but different polarities. So again, module manufacturers need to be aware to include both testing, appropriate testing, and mitigation measures. Now, the thing with testing for PIDS was quite straightforward. You need a chamber, an environmental chamber, and apply high voltage. PID polarization is actually mitigated quite significantly by UV, by light in the field. And it's quite difficult to catch it in the field and measure it. So doing realistic testing, because the high voltage will degrade the cell, but the light will mitigate. So it's quite a fast and frequent change in basically cell efficiency to this effect. So doing a realistic test requires you to apply both light and high voltage to the module when you test it in the lab, and also you need to separate the front side from the back side, so you don't want to stress both at the same time. So testing procedures nowadays require electrolytic gel, transparent electrolytic gel that allows the light to come from both sides. One side is grounded and the other side is set at a high voltage. And recent testing done by some of the colleagues in subtask shows that the higher the light, this will affect basically, if you do the test in dark, the cell will degrade quite fast. But if you simulate the actual real conditions where there is some light on the backside, degradation is slower, because voltage in a string will only occur when there is some light on the panels. So testing it is not so straightforward. Another degradation mode that has been an issue for some years is LID, and its newest form, LETID. LID has been around for many years and is well known. It occurs in the first hours of operations, and it causes a rapid decrease in power and then some recovery. However, when people were testing for LID and they started to do the tests at higher temperature, they noticed a secondary effect that has a much longer recovery rate, which is the light and elevated temperature degradation. And this one is not so well understood, but both of them in certain cells can cause quite a lot of power loss. LID was initially, or was mainly affecting CZ P-type made solar cells, and it was due to formation of boron-oxygen complex. There was oxygen impurities from the manufacturing process combined with the boron, which is used for doping. So the solution there was to replace the boron with another element from group 3, which was gallium, or to use a manufacturing process that produces more pure silicon. So gallium doped CZ ingots seem to be the solution, and they fixed the LID. But as you'll see in a few slides, it seems to reignite the LETID in these gallium doped wafers. LETID, however, also affects other types of silicon wafers. But this work is mostly focused on the gallium doped one, which is kind of the solution to LID. So based on some accelerated testing done by Michael Winter and his colleagues, they first did the normal LETID test at 80 degrees Celsius and 1 sun, and they could see a quite rapid degradation in power, only by about 0.7% relative change in efficiency. And this was recovered, but it took about 1,500 hours to recover. So gallium doped silicon is quite resistant and much better, both to LID and LETID, than boron doped one. However, when they did the test under higher temperatures, they could see much faster and greater degradations in the solar cells, up to 2% relative efficiency degradation at 140 degrees. Now you may think, okay, 140 degrees cell temperature, that's quite unrealistic. Yes, except the cells which are shaded. And you'll see in some of the other presentations, cells in the newer modules, which are shaded, can reach higher, these kinds of temperature in operation. Another interesting failure mode, this is work done by Jalen, is cell cracks in the newer types of cells and module technologies that you have. And this is kind of a combination between half-cut cells and shingled modules. Shingled modules can be done in different ways. One is by having half-cut cells and tilling them and connecting together soldering together the bus ribbons. It can also be done with cells which have smart wire connection. The purpose here is to basically reduce the space between solar cells to increase the overall efficiency of the module. And kind of the true shingled modules is to take a solar cells, cut it into 5 or 6 strips, and then connect these strips with electrically conductive adhesive. And then you would get a nice looking module like this. Now, in this work, all of these different solutions to create shingled modules show some issues with cell cracks. So the first one, for the tilt shingled modules, people started noticing these kinds of black spots after installation or after transportation that grew quite quickly, and they were localized to the center of the module. Doing a bit of investigation, they found out that they are caused by the connectors that were pressing on the modules during module transportation. So a quick fix for this was to wrap the connectors after they were manufactured and in the field, ask the installers to handle them carefully, but it's not always happening. Then they also seen like small cracks that usually are not so significant in production. After the modules were packed and shipped internally, before delivery, can have these cracks grow quite fast. So you would expect that half-cut cells, which are kind of known to be a solution for cell cracks, would be more reliable, but this is kind of the opposite of that. Cracks were also detected in doing regular accelerated stress testing, qualification testing that we do for modules in these shingled, tiled modules. And the cause for that seemed to be issues with the gap between the cells that were too tight, so that were occurring in the stringing process. If we look at smart wire technology, it seems that the lamination process can have the pressure there can have an effect, detrimental effect, and cause the formation of micro cracks in certain types of modules. So in this experiment, they were laminating at different pressures, interrupting the process, doing an EL image, and then you can see the formation of solar cell cracks at specific locations in the modules. So and lastly, the true shingled modules using electroconductive paste, those also can be affected by cell cracks. These are some modules from the field. Although they look pretty bad, due to the way the cells are connected together, this will always kind of provide a current path from the cracks to the electrical circuit of the module or around the crack, making it look worse than it actually is. And this is also supported by accelerated stress testing, where they induce these kinds of cracks. They also did an analysis of where they occur, and they occur around where the paste is located, where the ECA pads are. And they found out, like for a module where around 50% of the pads, of the connection pads, were were found to have cracks, and they did this in thermal cycling. This only caused about 2.3% degradation in performance. So it looks bad, but it wasn't that bad. The last failure mode I want to talk about is hot cells. This was work done by Mark Kangas from ISHF. And this is for the new module designs with half cells and series, parallel series type of connection, where the tests that we have, the hotspot tests that we have nowadays are not testing for these new designs or potential problems that these new designs have that the old series connected designs did not have. And so basically what happens if parts of the cell is shaded, there's a lot of heat dissipations from the rest of the cells in the same substring in that cell. And the power that is being dissipated is also increasing with the bifacial current gain. So we have bifacial cells now, very high efficiency, so very high currents, and they are also made from larger wafers, which all contribute to having more power dissipated and therefore hotter cells than we've been used to with the older module designs. And there's been work done both in simulation to kind of determine what is the worst case scenario, so the worst kind of shading that we could have. And they found basically the worst case would be if you have 20% of one cell shaded and the module is operating close to short circuit, then you have, for this type of module, almost 68 watts energy dissipated. And this would translate at around 130, 40 degrees Celsius. Now, in field operation, the modules would operate at MPP, and the worst case would be if you have two cells from the two module halves, parallel halves, in symmetrical positions. And this can be caused by bird dropping. So if you're unfortunate that you have such a situation, this can cause quite a high and hot hotspot there. And this is also supported by accelerated stress testing, where they found for different shading scenarios, similar to what you saw there, that the hotspots in the modules can reach quite high temperatures, even higher than they had in the simulation study. Now, one important thing to note is that these have only been found in the lab, so there's no documented cases, as we know, for modules in the field where they were caught with the thermal camera having, 150 degrees or thereabouts. How are we with time, Peter? 3 minutes, and very fast. So this was some of the work occurring that is being prepared for a report. We're also here at Research together with European Energy. We're had this year quite a big effort to do a degradation study on bifacials, where since bifacial panels are not so new, there's not a lot of information how they degrade in the field. So over the spring and summer, we took down some of the older modules that were installed 4 or 5 years ago, together with some of the newer ones, like the large format ones. And we tested about 160, 70 modules that we took down in our lab, flash tested and yield. There were different types, frameless, framed modules. All of them were P-type. Most of them had 3 to 4 years operation, with the exception of the recent ones, which are the newer modules, or the first generation of the high power, high voltage modules that we have in the field. And what is interesting to see here is the power, the PMP, where you can see most of the modules were around an average of 0.5 per year, or you can also see them here. The longies, the newer ones, were quite robust. The Trinas and the LR4 were about the same in degradation rate, whereas for the first generation of the large format modules, they had quite a large degradation rate. And from our investigation, it was both on the front side, but mostly on the rear side. We could see up to 50% degradation on the rear side. Initially, we thought it was PID. Now we are not so sure anymore. Could be a new degradation mode. Could be some type of light-induced degradation or UV-induced degradation. We are still in the process of analyzing the data and kind of compiling together with the other failures that we notice also in the other modules. Both finger breaks, dark spots, something happening with the cells and encapsulants that we haven't really seen in other types of module yet. So we are in the process of confirming. So that was one part. The other part is because the technology is changing quite fast, and now it's these high power modules that are coming and are becoming the workhorse for new plants. We've replaced the modules that we've took down with kind of the main technologies available to us last year or this year that we purchased. It's all 600 and above watts panels. 3 of them are P-type, 1 is N-type, which we installed. 3 of them we installed in the field. The N-type is still at the lab for accelerated stress testing. So some of the modules and these will deploy soon. And some of these, or 3 of these, were sent for chamber testing. Since we don't have a chamber here, we're sent to Fraunhofer for both for PID testing, damp heat testing, and mechanical load testing. I think the test is about to finish now. We have some intermediate results. They didn't show a lot of PID degradation, but some of them showed issues with static load testing, especially one type of modules in particular. When they were clamped, according to 2 of them were tested from the same type. Both of them failed, whereas the other types didn't fail. So there seems to be some issues there. So we hope that in the next few months we are able to compile this and report to publish. And that's it. Thank you.